Welcome to EDU World Space.
Alright guys, we're doing problem 110 of chapter 9 in Chemistry Central Science. So using the valence atomic orbitals of hydrogen and fluorine, and following the model of figure 9.46, how many molecular orbitals would you expect for the HF molecule? So hydrogen has one valence orbital, and fluorine has four valence orbitals. So hydrogen is going to have the 1s orbital, and fluorine is going to have 2px, 2py, 2p, 2pz, and 2s. Therefore, you would have 5 orbitals, and this would create 5 molecular orbitals. Now, for B, how many of the molecular orbitals from part A would be occupied by electrons? So, hydrogen has 1 valence electron, while fluorine has 7 valence electrons. So there would be 8 total electrons, and in the atomic orbital for HF. So 8 electrons would be filled in, that's 8 electrons would be filled in 4 of the 5 molecular orbitals, because since 2 electrons can fill a molecular orbital, then you're going to fill all 4 of your orbitals before you hit that 5th orbital. Okay, now C. It turns out the difference in energy between the valence atomic orbitals of H and F are significantly different that we can neglect the interaction of 1s of hydrogen and 2s of fluorine. The 1s orbital will only mix with 2p orbital of fluorine. Draw pictures showing the different orientation patterns of the 3p orbitals on interacting with a 1s orbital on hydrogen. So this is going to be, it's kind of difficult to draw on a 2D map. So this is going to be a bit tricky. So let's say this S and this. That's like S. This is going to be our P. This is going to be our, I guess we can call it our SPY. This is going to be SPX, and this is going to be SPZ. So our hydrogen is going to interact with this. It's going to have this kind of overlap between the p orbital and the s orbital. Now, they want to know which of the two p orbitals will actually make a bond with our 1s orbital, assuming that the atoms lie on the z-axis. So let me draw like an xyz axis. This is our Y, this is our X, and this is our Z. Z. So it would look something like this. In fact, let me just do green to. So our hydrogen is going to look like something like this. It's going to interact with the p's with our p orbital on the z-axis. So D. In most accepted pictures of HF, all other atomic orbitals on fluorine move over at the same energy into the molecular energy. So in the most accepted picture of HF, all other atomic orbitals on fluorine would move over at the same energy onto the molecular energy orbital diagram for HF. These are called non-bonding orbitals. Sketch the energy level diagram using for HF using this information and calculate the bond order. So here's our H orbital, here's our P, here's our fluorine orbital. So since fluorine is the only atom using p orbitals, that means we could theoretically only form one pi bond. So now we're going to put our electrons from our non-bonding orbitals into our bonding orbitals. We're going to put our sigma and our pi bonds, and then those last two electrons, we're going to put in our anti-pi bonds. So HF has a single bond. Like you literally can't form a double bond. You literally can't form a double bond with hydrogen. So those two. So the fact that we have two electrons in our anti-pi orbital, that cancels out the pi bond. So that eradicates any double bond from forming. So that means we're going to have a bond order of 1. Now, looking at E, look at the Lewis structure for HF. Where are the non-bonding electrons? So this is our Lewis structure. So the non-bonding electrons are going to be on our more electronegative atom, which is going to be our fluorine. These lone pairs, these are our non-bonding electrons.